So first, a few things. If you're new to design of experiments, please feel free to take advantage of all the free resources available to you. Our Studies internet site has all kinds of beginner resources, all of the webinars that we've given, articles relating to design of experiments, and tutorials for using the Design Expert software. We also have a new YouTube channel where we're putting up different various and sundry videos that we've recorded over the years. Not full yet, but it's getting there. Also, don't forget about things like the LinkedIn groups. There's a design of experiment group that's dedicated to answering questions about design of experiments. The ASQ Statistics Division has more general statistics in DOE. And of course, our little LinkedIn forum is where we have our friends and clients come ask us questions, and we put fun things out there as well. So first off, what is design evaluation? Well, in simple terms, it's a set of tools to determine the capability of a design. We display the alias structure that tells us what effects can be cleanly estimated. We show how the degrees of freedom are spent. The runs pay for the model and upgrades to the model. We present the correlation statistics about how imbalanced and non-orthogonal the design might be. And we expose the matrix measures, which are generally things only statisticians care about. So where do you get design evaluation in our software? Well, first off, we provide it throughout the build of many of our designs. When you build a really small 2 to the 2 4-run factorial design, there's a warning that's displayed regarding not having enough information to test all the effects. When you do a 2 to the 3 factorial design, it's built warning. A warning comes up that says you don't have enough power to estimate effects because it's a small 8-run design. When you do fractional factorial designs, we show you the alias structure. And all factorial designs include a stop where power can be estimated. The rest of the discussion is going to be concentrating on the evaluation node, which shows up after you build a design and is available once you have information in the factor columns. Evaluation is usually used before data has been gathered, but can be used post-analysis to verify the usefulness of the model. Which brings us to the point that evaluation needs a model. And that's the first tab you'll see when you go to the evaluation node. On it, you have the option to set the order. Gives you all of the terms in the quadratic, cubic, linear, or just the mean model. It's an easy way to select all of those terms that show up down in the terms list over here on the lower left-hand corner of the screenshot. The model switches what types of terms and orders will be displayed. The choices there are polynomial and factorial. Most of the time, design evaluation is used for a polynomial model, but not always. Add term is what you use to add higher order terms one at a time, rather than trying to find them down towards the bottom of the list. For instance, if you want to add the a squared by b squared by c squared quadratics interactions, you can just type it in rather than trying to drive all the way to the bottom of the list. The response defaults to the design only, which treats the evaluation as though all of the runs are completed and will be in the final data set. If a response has data, then an individual response can be selected, and we use this to evaluate what happens when there's missing data in a particular response. How does it impact the evaluation? And last but not least, the terms list shows which terms are in the model, which is the large green M, error, which is a small blue E, or excluded, which is sort of a pink reddish X. You can double click and right click on the individual terms in that list to change where they appear. Once you select all of your model information, you can click on the Results tab to unleash the evaluation. There's a Bookmarks tool that shows up on many of our reports, and the one for the evaluation is particularly useful. It lets you find where to go next. When you click a button on this Bookmarks tool, it'll move that section to the top of the screen. The Popout View down at the bottom here creates a clone of the evaluation report with its own Bookmarks tool, and it will stay open even if you leave the evaluation node. It lets you look at the evaluation and the design simultaneously, or evaluation and analysis simultaneously. Aliasing shows the relationships between the non-excluded terms on the Model tab. When you click it, you will get a list of the terms, which are in brackets, and beyond the equals to are a set of terms in the model that are aliased with each other. The degree of freedom button shows you how the information from the design is distributed through the analysis. Basically, 1 degree of freedom comes from each run, and the table shows how each one is used to compute coefficients and noise. The degrees of freedom used to compute the intercept term, if it's part of the model, will not be displayed here. And by default, they're in the model. So this is a 9-run design, which I can tell from the corrected total. It says 8, but that mean is automatically estimated by the intercept term. And I'm fitting up to 8 terms with those 9 runs. That leaves nothing for the residuals and lack of fit. If you see this, if you have no residuals, there's no ANOVA tests. The terms and power section has correlation statistics. A VIF of 1 is ideal, which indicates no correlation between the terms. The power is the probability of detecting an effect. The size of the effect is measured in terms of standard deviations, also called the signal-to-noise ratio. We use that to put it through the power formula that's been developed, and we compute the probability of detecting an effect with a particular design. The leverage of a run depends on where it and other runs are located in the factor space. Runs with high leverage have more influence on the model than other runs. High influence or high leverage means it's off by itself if you think of the runs as distributed through Euclidean space. In this case, most of the runs are equally distant from each other, thus have the same leverage. The center point is relatively close to all of the other runs. It's in the middle. It has lower leverage, less influence on the model. And matrix measures are statistics used to compare designs to a standard or each other. When you click that button, it'll push this table to the top of the report, and you can get these numbers to compare to a standard, or if you have 2 designs open, you can look at one and the other. Generally speaking, the lower numbers are better, except for G efficiency, where the higher number is better. And last but not least is the correlations. The correlation plots are another way to show the relationship between terms in the model. The ideal design has a completely uncorrelated structure, such as this. Now, this only happens with factorial designs and interaction models. All of these off diagonals are 0. Of course, every term is correlated with itself perfectly. When you have response surface designs for higher order models, it's impossible to make everything uncorrelated. Well, you can, but it takes an infinite number of runs. Over here, you have some correlation among these quadratic effects for this second order quadratic model for 4 factors. Now, the main effects are completely uncorrelated, but the quadratic terms are correlated. Moving on to a more fractional design, this design is not ideal for all the terms, but it will work for a subset of the terms. Notice that the main effects are uncorrelated with any of these second order effects, but the second order effects are correlated with each other in some cases. You can tell you have this situation of a supersaturated design when these two correlation plots are no longer the same size. There isn't enough degrees of freedom to estimate all of these terms. Only a subset can be estimated. Now, it's arbitrary which ones you pick eventually in the modeling, but there are only a certain amount of degrees of freedom available to do it. Now, there's to be some bonus points awarded if you can tell me what design was used to produce this graph. You can put that answer into the questions. Make sure you form your answer in the form of a question, and we'll see how you all do. So the next step would be, when do you use it? When is design evaluation useful to you? Well, there's 4 basic times. And the first one is to make sure the design is able to meet goals. You built a design. Is it going to be capable of getting you useful results? Now, able to meet goals has a lot of things that go into it, more than what's even on this screen. But these are the 7 basic things that we talk about. First off, can the design actually fit the model you need it to? Second, is there any information about the residuals? Is essentially what that lack of fit test is telling you. That, of course, requires you to have more unique design points than coefficients in the model, and some replicates in there to give you a pure error estimate. We'll concentrate on those 2, along with number 6, generate useful information throughout the region of interest. So what's useful information? Well, it depends on what kind of design you're working with. With factorial designs, you're generally doing screening and characterization, and your emphasis is on identifying factors that have effects. If you change this factor, the response will change. For this purpose, we want to look at power is the metric we want to use to evaluate the design. If you're working with response surface methods or mixture designs, then the goal is usually optimization, which is either finding the best combinations or sometimes finding the failure conditions using a model developed through a design. We want to concentrate on how well does the surface represent the true behavior. And for this purpose, we want to look at precision of the model estimates. How good are the predictions? So power is the probability of a true effect testing as significant on the ANOVA given some expected noise. Power is calculated both upfront as the design is built and as part of the evaluation report. The upfront makes use of information about the difference to detect, or how big of a change does the response need to have before you care? When does it become a critical change? And some estimate of how much noise will be showing up. On the evaluation side, for instance, if you've already built the design and you're trying to evaluate the power after the fact, the evaluation node needs to be set up correctly to show you the power. First thing that needs to happen is the order needs to change to main effects. You can also use linear effects if the model type is polynomial. Then you can click on the Options button to choose your signal-to-noise ratios to estimate. Now in version 9, there's 3 options here that you can enter. The signal is the minimum size of a critical effect. What's going to make you claim that you've got an important factor? The noise is the unexplained variation in the system. And the best way to think of it is give me a good estimate for what the standard deviation will be on the ANOVA once the correct model is fit. A good surrogate for that is what's the standard deviation in the process when nothing changes. You divide the signal, the size of your required effect before you care about it, by the noise to get the value to enter. Change at least one box to match that signal-to-noise ratio, and then when you click on OK and go to the Results tab, and click on the Terms Power button, you will get an estimate of those individual powers. For a design to be considered capable, we recommend a power of 80% or more. This design isn't capable for small effects. It's too small of a design. Precision estimates using response surface designs are best done using the Fractional Design Space FDS graph found under the Evaluations Graphs tab. You skip right over results if you want. Set the model type to polynomial, usually if it isn't already, and change the order or terms to match what you want to evaluate for. The number of terms in the model will affect the Fractional Design Space curve. On the Fractional Design Space graph tool, you want to change the D to the plus-minus amount, otherwise known as the margin of error or interval half-width, that provides acceptable precision. People ask me all the time, how do I pick my D? And my response is, well, think about your response. Let's say you were expecting a response level of 50, whatever the units are. Is plus or minus 50 okay? Or is it plus or minus 5, plus or minus 1? When does it become comfortable for you to report that margin of error? That's the D you use. Change the S box to represent the unexplained variation in the system. And again, think of that as the best estimate for what the standard deviation will be on the ANOVA once you fit the correct model. So for this graph, using a different design, a better design than the one I just had evaluation for, using a D of 5 and an S of 4, I get a D over S ratio of 1.25. And for this design, about 82% of it is capable of giving me a confidence interval no more than plus or minus 5 units wide. It's a way we use to manage the expectation and size the design. Once you remove terms from the model, the post-analysis precision will usually be better than for the whole quadratic model. Now, if you want more details on the topics about sizing the design, see Brooks Henderson's October 2013 webinar, How Many Runs Do I Need? How to Use Power and Precision to Size Factorial, Response Surface Method, and Mixture Designs. It's out here at our normal website. Now, another thing that the evaluation is used for, and this is often post-experiment, is check the impact of design modifications. What happens when the levels change and/or runs are not completed? For this example, I started with a straightforward 2 to the 3 full 2-level factorial design that has the 8 vertices in it, corners of the cube. This design starts out balanced and orthogonal. However, looking at it and applying what I know about the process, I determined that the extreme low and extreme high vertices need to be modified because those conditions won't produce meaningful results. So what I did is I changed the -1, -1, -1 to -half, 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 making it a little bit less extreme. And for the high vertice, all high, I made it a little less extreme in a similar manner. It's now no longer balanced and orthogonal, so the question is it still useful? Well, evaluation has our answer. If you go to the evaluation node, the first thing you'll see is no aliases found for the 3FI model, three-factor interaction model, and these correlation statistics. When you're working with aliasing, no aliasing found is the best thing to see. However, when you have some fractional designs, you'll end up with first and second order terms being aliased with third or higher order terms. This is acceptable for characterization and optimization. Second order terms, in smaller designs, second order terms might be aliased with other second order terms. This is acceptable for screening designs where the goal is to detect important main effects. Notice though that the first order effects, your main effects, are aliased with third order or higher terms. When first order terms are aliased with second order terms, it's only really acceptable for verification designs where the assumption going into the experiment is there won't be any effects. And if you don't detect anything is significant, then your assumption is showing correct based on some data. Now, when you do this, when you look at power, if you compared this crushed design to the full factorial design where all the vertices were run, the power is going to be lower even though there's the same number of runs. That's what making it non-orthogonal does. And remember, when you're looking at power on the evaluation, set the model to main effects. When you look at the VIF column, it's no longer all 1.0, which is the ideal. However, small values that are 10 or less are not a cause for concern. Values between 10 and 100 indicate your orthogonality is compromised. Values from 100 to 1,000 indicate severe compromise, and over 1,000 is bad. It might not even be possible to obtain a model. Now, when you're running a mixture design, ignore all of this correlation statistics. Mixture designs are a special case. They're a kind of response surface design, and you should be looking at the fractional design space to see the effect of modifications, not the terms and power. So when you look at the fractional design space for this design, the modified design's fractional design space curve is not as flat and low as the unmodified designs. This is mostly happening because the design can still predict at the original vertices. We just changed those runs, we didn't restrict the predictions. The predictions will be poor beyond those halves because there's no data out there anymore. Now to get these two graphs like this, I copied and pasted one over the other in this PowerPoint presentation. For a second example, when we're going to lose a run or two, same design as the start, but the extreme low and extreme high vertices were left in. That's because there was no effort made to manually evaluate the design. That's one of the most important parts of evaluating a design is you looking at it. Take the time to go through each run to make sure you're going to get reasonable results. If you don't, then you might end up botching runs. So in this case, those two runs failed to produce a meaningful response. We had to drop them. So it's now a 6-run design instead of 8 runs, and it's no longer balanced and orthogonal, so is it still useful? Following the rules that we outlined earlier, the second-order terms are aliased with other second-order terms. This is acceptable for screening. We can still get information about how important individual factors are, but we're not going to be able to get useful information from the data alone on the interactions. We can also see how well an existing data set will perform. Often there's data that's been in existence for years. Can we analyze it? Well, you can use a historical design, copy and paste your existing data set in Design Expert, and check it out with evaluation. Good news is the checks are pretty much the same as evaluating design modifications. The difference is if there are problems with a design, you build a new design. You change those extreme values, restrict them a little bit. You rebuild the design with constraints. But if there are problems with existing data, there's some other different options. Number one, you can augment the design to add the runs necessary to make the design able to meet all those goals we showed you before. You can also use your subject matter knowledge to decide which factors are the true drivers of the response changes, then delete the other factors. If factors are correlated with each other, you can't really tell which one's driving the process. You get to decide which one is actually the driver and delete the other ones. Which way you go depends on what you know. Another thing that you can do with evaluation is compare designs, which is another thing only statisticians actually care about. So the best design. The goal of eye optimality is to minimize the integral under the fractional design space curve, which makes it lower and flatter. This provides a more precise model over more of the design. The goal of a d-optimality is to maximize the determinant of the X transpose X matrix. This minimizes the joint confidence interval volume for the coefficient estimates, which improves the power of the design to detect significant effects. If you look at the fractional design space for these two, as I stated, the eye-optimal design's goal organizes and picks runs that lower and flatten that fractional design space curve. The d-optimal design doesn't care. It cares a little, but that's not the whole story on the fractional design space curve. That's what the matrix measures are for. Now, as you can see over here on the left, the eye-optimal design generally has lower numbers than the d-optimal design, except for the d-optimality criterion and that determinant. These are lower for the d-optimal design. So the best matrix measure to use depends on the goal of the experiment. If you're trying to optimize and get a precise model, use the I-optimal design. If you're looking to find effects with high power, use the d-optimal design. The truth is, if you use the wrong optimality, it only has a microscopic effect on your actual results. However, we might as well get what we can, given that we have nice software to build such a design. So, unleashing the evaluation. First thing to remember is don't forget that you know things that statistics doesn't. Take the time to look the design over. Fix any runs that might be a problem, then use the design tools to figure out how capable your design is. Use the evaluation tools before starting the experiment. It's much easier to prevent problems than fix them. And use the tools when the experiment doesn't go as planned. Modifications to a design may or may not cause a problem for the analysis. The evaluation tools provide a way to check. And use the tools when you already have historical data. If the data set has similar structure to a design, then it analyzes like a design. If it doesn't, then it won't, and the problems will need to be fixed. So thank you all for attending. I'll keep the webinar open for a little while to receive and answer questions. And of course, feel free to email any questions about the presentation to webinar@staties.com. We will reply as soon as possible. All right, we have a question out there about explaining the difference between aliased factors and correlated factors. Well, aliased means that there's linear combinations of the factors. That means that they model each other better than they model the response. And sometimes it's perfect, and that's what the perfect aliasing does. That's when you see no coefficients, either -1 or all +1. Correlated means the structure mimics each other. Now, perfect correlation is aliasing, if that helps. All right, a couple more questions have come in. Let's see, RSM design, and the FDS shows not good enough. The FDS score is less than 80% of the design. Basically, what the evaluation tells you is design's not really capable of giving you good information. And it doesn't tell you where to add runs. At that point, if you don't already have data in your response, you build a new design with more runs, is one way to improve the fractional design space. More runs will always make that fractional design space curve go down. You can also manage your expectations. Okay, so plus or minus 5 isn't capable. How about plus or minus 8? That's another way to make it more flexible that way. Lots of things you can do, and that other webinar that Brooks did for sizing a design has all of the details you'll need. Standard error plots. They still exist in the software, but the fractional design space, I mean, when you're looking at the standard error plots and you have more than 2 factors, you can only really see a 2-dimensional slice of your surface. Where the fractional design space condenses everything to that 1-dimension curve. You can see how it works. Now the standard error plots will give you location of bad predictions, where the fractional design space just tells you you have them. For evaluating a design, the fractional design space curve is much faster. And then for evaluating your predictions around your optimums, that's when I bring in the standard error models as well. Question about why using a main effects only. Well, technically you don't have to use main effects only. However, we've made a decision here at StatEase that when you're evaluating for power and you have 4 factors, out of the likely candidate set of effects, there's going to be about 4 effects that are significant. So we made the decision to evaluate power for the main effects. If you want to manually include second order terms, third order terms, you may. We'll estimate the power for those along with all the other terms in the design for you. But generally speaking, we're trying to make it a little bit realistic for what most processes will do. All right, it looks like the questions have dried up and many folks have left. So with that, feel free again, send any questions you have. Oh, the bonus points answer. Thank you for reminding me. A couple of you threw that up. The bonus points answer. Let me go back up to that. The bonus points answer for what design produced this graph. This was a 4-factor, 9-run definitive screening design. Main effects are clear, but the second order effects may be problematic. All right, if there's no further questions, again, feel free to send your questions to webinar@staties.com. We'll answer them offline as soon as we get them. Thank you for coming. Have a good day.